Hey everybody, welcome back to A View from Earth, brought to you by the Fisk Planetarium at CU Boulder. Hope you're doing well and staying safe. Now, as with the rest of the university and many public spaces around the world, this theater is closed for the foreseeable future due to COVID-19. However, we are still so committed to bringing you astronomy and education that we've started a whole host of free online offerings so that we can stay connected and keep bringing you the FIS content that you know and love, plus some new stuff like this podcast. So thanks for tuning in and learning with us here today. My name is Tara. I'm a planetary scientist and a CU alum. I'm also a presenter at Fisk and the outreach coordinator. And my friend Colin is here with us too. Say hi, Colin.
Hi, Colin. Haha, it was a joke. Hey, I'm Colin. I'm an undergrad at CU. I study astronomy, and I also work at Fisk, hence you hearing my voice right now on the podcast.
So today we are talking all about the sun. The sun, of course, pretty important for life here on Earth. It doesn't just give us heat and light, though. It also gives us some other very interesting and maybe sometimes dangerous things. So we're going to be talking about all of that with one of our grad students, Chris Gilly, and also Dr. Ben Brown, who is a fluid dynamicist. He's got a lot of really interesting things to say. So we're going to play some excerpts from those interviews for you. But first, the news.
And here to deliver the news to us today is Jordan Marski. Hey, Jordan, thanks for being with us.
Hello. So I'm here to talk to you guys about today. The topic is the sun trying to kill us, which is pretty ridiculous question because I don't think the sun is like trying, but there are definitely concerns to be had with things that the sun will do. Eventually the sun will make the earth inhabitable in about 5 billion years. Once the sun burns through all its hydrogen, it'll enter the next stage of its life where it'll become a red giant, and its outer surface will start to expand and eventually it'll swallow Mercury and Venus and possibly Earth, but that's not quite as sure. But regardless of whether it swallows Earth or not, it'll almost certainly make Earth uninhabitable, as will just be so much closer and will make the surface hotter. But that won't happen for another 5 billion years, so we've got time to try and do something about that, like trying to get on a different planet or something by then, hopefully. But a more threat that could possibly happen like sooner than that is caused by solar flares, and which are often accompanied by coronal mass ejections, which are basically just huge bursts of energy that shoot out into space, and it can shoot out like just high energy radiation or plasma from the surface of the sun. And these are usually caused by the intertangling of magnetic field lines from the sun's surface. And while these bursts of energy are enough to seriously injure or even kill life, we're usually protected by the Earth's magnetic field, which shields us from feeling the effects of these kinds of things. But it could potentially disrupt things that are in orbit. So like any astronauts who are in orbit, like if they were directly hit with one of these ejections, they could be seriously injured. And it can also injure satellites or electrical grids on Earth, which, as you can imagine, because of how intertwined our society is with technology now, could definitely lead to some serious problems if everything just went haywire all of a sudden. Yeah, that could lead to a potentially apocalyptic scenario. Another thing that could happen, which is kind of frightening, is the idea of geomagnetic reversal, which is when the north and south poles of the Earth switch, basically. And this has happened many times throughout the Earth's history. It's statistically random when it happens, but it's happened about 180 times over the last like 83 million years, which gives an average of about 450,000 years, which is sooner than the last one happened. So technically we're overdue, but as I said before, it happens pretty randomly statistically, so don't really have a good guess on how like when that could possibly happen. But the average duration of these reversals usually lasts around 7,000 years, which would be enough time for like coronal mass ejection to happen. And if that were to happen during one of these reversals, there would be certain places on Earth that if they were like under the North or South Pole and got directly hit, could be left vulnerable because they wouldn't have as much of the magnetic field covering them, and could leave those areas vulnerable to feeling the effects of the radiation, and could possibly like damage or like even kill like life that was caught in that crosshair, which would be just incredibly unfortunate and like worst lottery win ever that could happen.
Yeah, that's some pretty terrible luck.
Yeah.
You know, it's interesting. Aside from the 5 billion years between now and when the sun kind of moves into the next stage of its life, the other two events, you know, the CMEs and the polar switching on the Earth, you know, we talk about these events like there's this huge amount of time between them, but astronomically speaking, that's the blink of an eye. You know,
oh yeah,
we're just moving through time. And so it's kind of curious to think about space news to humans. You know, we can think about, oh, this happened in the past week. That's recent. But, you know, in an astronomical sense, if it happened in like the last, you know, 100 million years, that's like instantly in the past. You know, that was like a couple minutes ago. And so it is interesting to think about, like, you know, that these things are happening pretty regularly, but on the scale of human life, there's lots of time.
Yeah, and I think the last known like geomagnetic reversal on Earth occurred around 750,000 years ago. So pretty long time, but again, on astronomical scales, that's like not a huge amount of time.
Right. Yeah, 750,000 years, nothing.
That's
nothing. So
on the plus side, I did read a thing out of Harvard this last week saying that they did a study on tardigrades, little water bears, that they would survive any cosmic catastrophe that could possibly happen to the Earth until the sun explodes and our oceans boil away. Up until that point, they're good. So tardigrades are gonna repopulate the Earth, I'm pretty sure.
Yeah, well, nice. Yeah. Good to know we've got backup in case we destroy everything.
Life finds a way.
Well, Jordan, thanks for giving us the news today. Astronomically relevant, and hopefully we will be safe from those statistics. Actually, statistics is on our side. Hopefully we'll be safe from the what's the opposite, the bad luck. Hopefully we'll be safe. Let's hope for good luck. There we go.
Bad juju.
Yeah, right. Okay, so now we are talking to Chris Gilly, who is a graduate student at CU Boulder studying waves that help heat the outer layers of the sun to millions of degrees. He is also interested in the sun-Earth connection and how what happens on the sun can affect us here on Earth, for good or ill. Gilly looks to use new technologies like the Parker Solar Probe and the DKIST telescope to further his work. Hi, Gilly. Thanks for being with us.
Thank you so much. Yeah, I'm glad to be here.
So to start things off, well, I'm going to go ahead and reference something from your website, which, by the way, can be accessed through the CU. If you just search like colorado.edu space Chris Gilly, you'll get his website. It'll pop up
You can also
there.
go to gilly.space, just gilly.space. Type that into your bar, and that's me. Yeah.
That's so easy. How did you get a .space suffix?
$50 a year.
Wow,
The
that's
.space
amazing.
domain. They've actually opened up all kinds of cool domains. One of them is .sun, but because of Sun Microsystems, that's actually very expensive of a domain to get.
Sure,
So I got
sure.
.space.
Gilly.space. That's perfect. That's super easy. That's GILLY.space. So
Sure,
on your website, on your website, Gilly, you mentioned that you study the way that light from the sun affects the rest of the solar system. Are you looking at, and obviously I don't want to say that you're lying on your website, but are you talking about light itself or other stuff that is associated with the sun, say the charged particles that we talk about, or like coronal mass ejections? What are you looking at as far as stuff from the sun affecting the rest of the solar system?
Yeah, so I study light. I did a lot of light research in undergrad as well. And in general, I just really like photons and how they work, how light works. Trying to imagine yourself as a photon traveling through space is, it's really wild, the consequences of that. So I'm interested in light. I understand light more than, probably more than I understand like plasma and stuff like that, honestly. But you're right, the actual light going out and affecting the solar system, I've written down a couple different ways that it does, some cool examples, but really I'm using light to understand the sun. And so, a lot of people do that. You look at the sun with a camera or a spectrograph or something, you get that light and you try and interpret it. But I would say I'm really working on the, how does that interpretation work? If I measure this, what does it mean? There are some basic steps that people take, oh, if I measure this, that means maybe it's so hot, it's this hot. But that process of going from I've measured light and now I'm trying to say something about the sun, it's rife with pitfalls. There's a lot of things you can do incorrectly, and you'll get a result that might not actually represent what's happening on the sun. So a lot of what I do, the title of my research is optically thin radiation is what I study. And so if you look around me right here at this sun picture, right, the sun itself is opaque. You can't see through it. But when you look up here in the upper regions of the sun, it's the atmosphere. Just like air, it's not opaque. And maybe light's coming from it and scattering off of it. But when you look over the surface of the sun, you're looking through a whole long column of plasma. And when you see this stuff right here, that's probably happening. Is it in the foreground? Is it in the background? Where's that going on? There's a lot of interpretation that has to be done there.
So aside from all of the calibrations and measurement uncertainties and stuff, essentially you are looking at how light from the sun affects the rest of the solar system, which obviously does. Light from the sun heats things up. It allows things to grow and allows us to see things. But are there any maybe really cool or really unusual ways that light interacts with the rest of the solar system?
Yeah, so I thought about this a little bit, and so I've got a couple things here. So starting with the boring ones and moving to the most interesting ones. So yeah, of course, the sun provides all of the heat and light for the whole solar system. Without the sun, it would be way, way, way colder here. And the planets would go flying off in all directions if the sun actually weren't there. But what's interesting is some of the coldest places in the solar system are actually closest to the sun. So at Mercury, some of the craters in the poles of Mercury have never seen sunlight ever in the history of the solar system. And so they're just some of the coldest places in the whole solar system. And that's surprising because Mercury is so darn hot right there. And also, just as an aside, Venus is hotter than Mercury, even though it's further away because it's got that atmospheric blanket. But the cool thing that I thought of for what's something that light is doing in our solar system that people maybe have never heard of. Have you ever heard of the laser on Mars?
No.
Yeah, so okay, light from the sun charges up the atmosphere of Mars until it starts lasing like a laser. And so when you measure radio emission from Mars, you look at it as a function of wavelength, and there's one wavelength where you get a whole bunch of light coming off of Mars. And so it's an atmospheric, I think it's carbon monoxide that does it, but it's an atmospheric maser, microwave amplification by stimulated emission of radiation. That's what laser stands for, by the way, light amplification by stimulated emission of radiation. It's a laser. But before anyone ever did that with light, they did it with microwaves. And so they were originally called masers. And so there is an atmospheric maser on Mars. And if you don't really know how lasers work, it's pretty cool. You charge up a crystal with energy, basically, and so that it's glowing. But then you put mirrors on one side, on each side. So when the light goes out the sides, it just goes away. But when it goes to the mirrors, it bounces back and forth through the crystal. And so it gets brighter and brighter and brighter every time. And then you put just a little pinhole on one side and bright light can get out. So the same thing's happening with Mars. You're charging up the atmosphere of Mars with energy, and then it's emitting light, and in one of the directions, probably parallel to the surface of the planet, that is able to travel far enough through that charged medium that it gets brighter and brighter and brighter and brighter until it's basically beaming a laser out in all directions from Mars, a lot of directions from Mars. So that's like the coolest, like weird, fun fact I can think of for what just the light is doing in the solar system.
That is fascinating. I never knew that.
Yeah, the Mars maser.
That sounds like almost like Avengers type or like superhero movie type thing. Like we're gonna supercharge the atmosphere with light and then turn it into a laser. I don't know. It just sounds crazy.
Right. So like if you want to do a superhero version, if you were to take some sort of spacecraft and put it at Mars and then beam energy through the atmosphere of Mars, that would be amplified. So if you were to pick that laser frequency, if you were to pick that and shoot it through Mars, it would be much brighter once it got out the other side. Now, I don't know if you can actually destroy a planet with that or whatever you want to do, but it will have that effect there. We talked about how light affects the rest of the solar system. one of your questions I wanted to address, you asked, what are some of the less obvious connections between the sun and the Earth? And so, people think about like solar flares, that's totally a thing. You think about like coronal mass ejections, there's active events that occur on the sun. But like, what does that do to us on Earth? For the most part, not all that much. But it can cause geomagnetic storms. So basically you can imagine like some giant ball of plasma is launched from the sun. It's coming towards the Earth. And when it hits the Earth, there's a couple things that happen. First of all, it's like a big magnet. So if you know anything about magnets, if you have a wire and you run a magnet past it, that's going to push the electricity in that wire. So you can generate current in that manner. So we've got tons of wires all over our planet, most notably the electrical grid. And so if you have an electrical grid and it's running at like 90% capacity, and one of these magnets pushes past the Earth, it'll induce more current in it. Now you're at 150% capacity and things start melting. But if you turn it off first, you're at 0 or like 10%, because you probably can't turn off everything, right? This magnet comes by, the ball of plasma from the sun, and it induces current, but now you're up to 80% capacity or something. All your wires don't melt. And so your electrical grid is safe. So the point is that if you react in time, you can save our infrastructure. And this is also true for spacecraft. If you turn it off, it's going to be a lot more resilient than if it's running, just because of that basic, like it's already running near its capacity. If you put more in there, it'll melt. So there's a couple cool points in there. Like the fundamental reason that my field exists, solar physics, at this point right now, it was mandated by Congress even as a national priority, is that we need to be prepared for these kinds of space weather events. So like right now, if there's going to be a tornado tomorrow, there's going to be a tornado watch or a warning, before that. If it's going to rain, maybe we know there's going to be a 40% chance of rain. We have this knowledge. We can even tell you next Tuesday, there's a 30% chance of rain. But with the sun, we have none of that. We can say, oh, over the next 5 years, it's going to be more active than the past 5 years. We can even say, oh, look, that's a thing right there. Like maybe that could do something eventually. but I can't tell you the chance that that will explode. I can't tell you, when it'll explode or predict it, hardly at all. And so the whole field of solar physics, or at least a big chunk of it, a big part of our job right now is to gain that predictive ability. And there's a lot of different ways people are working on that. People are trying to study how does the sun work at its most basic level, from the core to the edge of the solar system. And then there's people who are saying, okay, maybe we don't need to understand how it works as long as we can predict it. And so they're trying to apply like machine learning and all these other kinds of magic skills that people have that can maybe give us an idea that something might happen, even if we don't know why, or if we don't understand how the machine knows that's true. So yeah, it's a big part of solar physics is trying to say like, oh gosh, should we shut it down? And right now we've never even sent one of those alerts. Astronomy has this whole like system of alerts, and I'm pretty sure they use Twitter for a large part of it. So like something happens over there in the sky and someone tweets, oh gosh, this star is dimming, and silver alert. And depending on the level of the alert, all of these telescopes will automatically slew to it. There's even a telescope in space called Swift, and its whole job is just to point immediately to whatever it is that's happening that anyone has seen. So there's this whole global network of astronomers that are currently working to see what are called transient events, things that happen in space just for an instant and then stop. And it's hard to get a lot of data from those things because, they're gone after a minute. So we're working on making a similar system like that with the US and other governments, right? And if I don't even know who the top solar physicist is right now, but like if someone were to be like, Mr. President, we've got to shut down the system today, I'm not even sure there's a pipeline to make that happen. I don't know who has a red cell phone in their office, to call the president and shut everything down. But it's definitely a national priority to build that system at this time. Yeah.
One of these buzzwords with the sun and the way that the sun works is a lot of people talk about these coronal alphane waves.
Sure.
Which is a big scary word. Can you tell us a little bit about what that actually means?
Yeah, okay, so let me just start one step back from that. The basic problem is that the surface of the sun is really quite cool compared to the atmosphere of the sun. So like you can imagine it like a campfire. Like imagine you have a campfire and you're sitting right next to it and it's pretty warm. So you take a step back because you want to cool off. But now it's 1,000 times hotter and you burst into flames. That's not how fire works, right? Like that would be so weird, right? But that is how the sun works, because the sun isn't fire, it's plasma. And I've been reprimanded for calling it fire before. It's not fire. And the reason for that is that there's no chemical combustion occurring. It's not the oxidation of a fuel that's occurring. It's not a flame. And so the surface of the sun is about 6,000 degrees. And if you go just like only 50 million miles above the surface, which is just barely above the surface, it's now 2 or 3 million degrees. That's a factor of 1,000 almost, And so how does that work? How at all, And so we don't know, like humanity doesn't know that yet. But we're actually in the situation where we have thousands of ideas, and really we just need to take more data and figure out which one of the ideas is correct. So the main one that I study is waves. So the interesting thing is that the sun itself, interior to the surface, is quite dense, and then exterior to the surface is quite rarefied. It's the opposite of dense, right? So basically there's enough energy in the sun that it could heat the atmosphere. But we just don't know the precise mechanism. So the way that I study is these alphane waves. And basically, the surface of the sun is boiling. You can just imagine a boiling pot of water. And if you look at that surface, it's really quite turbulent. It's bubbling, it's moving a lot. But unlike the water, there are magnetic fields coming out of that surface. And so just like a guitar string, if you pluck it, there's a tension in the string, and it'll tend to revert back, and it'll go over, and then it'll come back and over and come back, and you get this wave, and we hear that as a tone. So that is a transverse wave. It's transverse to the direction, and that's basically what an alphane wave is. You've got, if you're watching the video, you can see in the background here, you've got all of this stuff happening on the surface of the sun. It's boiling, it's moving, and that energy is carried up into the atmosphere through these magnetic strings, these magnetic fields. So we know that there's enough energy in the boiling to cause the heat. We know that Alfvén waves exist, and they're there. We don't know how strong they are. That's really one of the big problems that I work on in my research. It's like when you're looking through this transparent atmosphere of the sun and you're trying to see, is this thing waving back and forth? Well, if there was just one, you could like track that visually with your eye. You can say, ah, yes, that's waving. But it turns out there's like 100 of them all in a row in this transparent medium, and they're all waving along the line of sight, sort of like this. And you can't really tell exactly what's going on in there. So a lot of the work to be done is in these new telescopes that are coming on, the DKI Solar Telescope, Punch, some of these other missions, Parker Solar Probe, even to some degree. They're just trying to get a measure of how strong these waves are. So what we would hope to see is that they're really strong near the surface and they get weaker and weaker the higher you go. And that would indicate that that energy is being changed from the wave into heat. And so if we can precisely measure how much those waves, it's called damping, how much the waves damp out with height, we can visually sort of see in that way where the energy is going. And so a lot of work is going into that. And my research in particular does address that question of trying to say, if we measure this, what does that tell us about these waves in the sun?
And I think that was an excellent way to sort of wrap up our time here. So thank you so much, Gilly, for joining us. That was fascinating.
Thank you so much for having me. I really enjoy all of these kinds of experience and just talking forever about whatever it is. So thank you so much for giving me this opportunity.
Yeah, thanks for coming. So now we are speaking with Dr. Ben Brown, who is an assistant professor and researcher at CU Boulder. He studies fluid dynamics in stars and exoplanet atmospheres. He uses supercomputer modeling techniques to understand convection inside of stars and how it builds and affects the sun's active magnetic field. This can help us learn more about the origins of magnetic field events like solar flares that could impact life on or near Earth. So thank you very much for joining us.
Glad to be here.
So we're gonna jump right in and ask you probably the easy question. So fundamentally, you study how fluid dynamics kind of helps generate magnetic fields inside of stars and planets. Can you give us kind of a high-level intro on how that works?
Yeah. So in both our Earth and the Sun, which is the star I study the most, though I like other ones as well, there are large-scale motions in the interior of the objects. In the Earth, we have large-scale motions in the core of the Earth and also in our atmosphere. And both of those sets of motions actually share similarities to similar motions inside the Sun. And we study all of these together because they all have fluid dynamical properties and do some similar things, and we try and learn from all of them. So in these systems, especially in the core of the Earth and in the Sun, you can kind of think of both of those round spherical objects as having a hot thing in the middle, a source of heat at the center. And that source of heat, as the heat comes out through the outer layers of the fluid object, it can drive that fluid into large-scale motions. We call those large-scale motions driven by heat and buoyancy convection. And they're a bit like what you get when you start boiling a pot of water on the stove. Just a bit before you start getting the bubbles of the boiling, which is like the water turning into gas phase and going up. Before that, you can actually see the water in your pot of water starting to do stuff like this. You're looking from above and seeing it like this, and you can see it doing motions. That's convection, where the hot water at the bottom is rising up and the cool water at the top is falling down.
So what is it about the convection that helps generate that magnetic field?
Okay, that's a great question, and one we don't really know all the answers to, but I'll tell you a little bit. So we think that the magnetic field in the core of the Earth, the one that gives us a North Pole and South Pole for our compasses to find, and the magnetic field generated inside the sun that shows up both as sunspots on the surface that we can see, and also as a large-scale north field, south field, like on the Earth that we can measure effectively with compasses in space, on satellites and other things. and also remotely from polarization of light from telescope observations of the sun, we think that both of those magnetic fields have to be maintained by a physical process. Okay, so why do we think that? So the center of the Earth is very hot. It's, if I'm getting my numbers right, I think it's like 5,000 Kelvin or so. It's about the same temperature at the center of the Earth as on the surface of the sun, about 5,000, 6,000 Kelvin on the surface of the sun. And the center of the sun's even hotter, about 15 million Kelvin-ish. And Kelvin, Celsius, they kind of count the same, right? But 0 Kelvin's like absolute zero, cold as it gets. 0 Celsius is actually at like 273 Kelvin. And from there on, they just degree Celsius and a degree Kelvin's the same thing. But on the other hand, like 6,000 is hot in whatever degrees you're in, and 15 million is even hotter. All of those temperatures are well above what we call the Curie point of any normal material. So the Curie point is where like a magnet on a fridge goes from being a magnet to being a lump of iron. So if you take a magnet from a fridge and you put it in a frying pan and you heat it up, at some point it stops being a magnet. It does that not at incredible temperatures. And the center of the sun and the surface of the sun and the center of the Earth, they are incredible temperatures. So the sun and the Earth don't have like little like iron bar magnets all lined up to give it a large scale field. So it's got to be something else. And what we've come to realize over sort of decades of study is that it's what we call a dynamo process. So it's a process where fluid motions, kinetic energy of fluid motion, create magnetic energy and large-scale organized magnetic fields. How that happens exactly, we understand bits of, but not everything of. So there's, for just like the fundamental idea of how a dynamo process works, the magnetic fields are almost a little bit like rubber bands when they're inside a charged fluid, a conducting fluid. So the liquid iron of the Earth's core, or the hot plasma, the hot hydrogen helium plasma of the sun, those are very conducting materials and fluids. And when those materials have magnetic fields in them, as the fluid moves, any magnetic field kind of acts as a rubber band in that fluid. And it can be stretched, which kind of makes it stronger, puts energy into the magnetic field, much like when you take a rubber band and you stretch it, you're putting tension into it. And you can also sort of take that rubber band, you can stretch it, and then you can fold it on itself, and then you can stretch it again and fold that on itself. And if you have these sort of stretching and folding motions, you can take a weak magnetic field and turn it into a very strong magnetic field. It's almost like making like layers of pastry or something like that, like making a croissant of magnetic field. You're like rolling it out and folding it over and rolling it out over and getting layers built up. Make a nice flaky magnetic field. Things, especially in the sun and the Earth too, get more complicated. That convection, in addition to making the magnetic field, it does some other things. So one thing that it does is it makes the sun rotate in some very interesting ways. Our sun has what's called a differential rotation. What that means is that if you look at the equator of the sun and you look at the pole of the sun on the surface and you count how long it takes for a thing to go all the way around. So we do this by measuring the plasma velocities. We also do it by watching like sunspots moving, and we watch like convective features moving. We watch lots of things moving because there's no like real fixed surface. So we can't just look for like, hey, when does Africa rotate around on the Earth, right? Or something. We have to try and, the measurement's a little hard on the sun. But we have a lot of different ways of measuring it. They all kind of say the same thing, including some really cool ones that I'll tell you about in a few minutes, about how we measure actually the inside of the sun where we can't see. So when we measure all of these, what we see is that the equator goes around faster in even how many days does it take sense, not even just a like miles per hour sense. The equator goes around faster than the poles. We look at the sun and we look at the equator. And the equator takes like 25 days, 25 Earth days to go one lap around the sun. 25 Earth days at the equator. Now we go look at like the pole and it takes like 35 Earth days to go around. So the sun, right, the equator is going around and the pole's going around, but there's this like big stirring shear on the large scale. Call that the differential rotation of the sun. And we think that that is built by the same small scale convective motions. We think that they actually build that large scale difference in rotation. We don't really understand how even that happens in detail. That seems to be especially an interaction of both the stratification of the sun. So that means that dense, deep, low density, high up. So that's a stratification, combined with the fact that the sun is a rotating body. Those two things together seem to contribute together to the creation of the differential rotation. Okay. That large scale differential rotation, that big like wind in a sense, where the equator goes fast and the poles go slow, that plays a big role in the dynamo amplification of magnetic field. Because if I now take a magnetic field that goes from the North Pole to the South Pole, there's my magnetic field, and I'm shearing it like this, I'm stretching that field and making it stronger. And the kind of funny thing is if you've got a field going this way and a flow going this way, the field going this way, the kind of field the flow makes, it's actually in the direction of the flow. And that field is the same orientation as the field that we see in sunspots.
So we're talking a lot about all of this stuff that happens like in the center of things, like stars. I know we can see some of that convection happening like on the surface, but how do we actually study the inside of the star?
That's a cool question. So Sir Arthur Eddington was a super famous astronomer back in the early 1900s. We have various things named after him. He was a British scientist, very well respected in his field. And at one point he said, you know, the one place we will never be able to, I'm going to paraphrase his quote. There's a great quote to go looking for. But to paraphrase it, he basically said, like, the one spot in the universe we're never going to get to see is inside a star like the sun. It's going to be forever hidden from our view. No chance of seeing it. I think that quote was from the 1920s, broadly speaking. By the 1990s, we could see inside the sun in detail. And in fact, we have made measurements of the inside of the sun that are accurate to less than 1% of uncertainty. How do we do that? There are kind of two different ways that I know of that we can see inside the sun. I'm going to tell you the really exotic one, and then I'm going to tell you the really simple one, which actually we learn a lot more from. So the really exotic one is, so the problem with the sun and seeing inside of it is that the surface of the sun is opaque. So the surface of the sun, we call the photosphere. The photosphere is the surface that light comes out of the sun. That's basically where you go from the sun being opaque below that level to being transparent above that level. So we see the photosphere, so we see the last opaque surface before it becomes transparent. Everything deeper in the sun, if I'm the center and you're the viewer and you're seeing my photosphere, if you see my hands as the photosphere, you can't see my face because it's buried under my hands and my hands are opaque. So if my head's the core and my hands are the surface, you can't see what's going on in the center of the sun. Man, it'd be really neat if there was some way of detecting some kind of radiation or something that came out of the center of the sun that would like thought the sun was transparent. There's a type of radiation that comes out of the center of the sun that the sun is transparent to. And in fact, we're transparent to too, and it's flying through us right now and through the Earth we're sitting under and pretty much all material known to man. It's a type of radiation called neutrino radiation. So we often talk about like radiation coming from the sun as photons. That's electromagnetic radiation. Neutrinos are a weakly interacting particle. Weakly there means in like the physics sense of weak. So like they interact with what's called the weak force. So I said photons are electromagnetism. They use the electromagnetic force. These weird neutrinos use something called the weak force, and they're extremely different from almost everything else we have experience with in this world. But like 100 billion of them are going through my thumbnail every second while I'm talking with you, and the same for you. Because almost all material in the universe is transparent to them. If you're super clever and you get a lot of material all together in one spot, then you can detect the occasional neutrino out of this incredible flux of them that are coming through you all the time. We have a couple ways of doing that. One of them is to build giant tanks of water, usually under mountains. So a very famous one in Japan is called supercomputer. It's a giant, giant tank of water, like just huge, absolutely huge. You can go boating on it, and your rowboat is small compared to the overall tank. And they use this tank, and they have instruments all around this tank that look inside this tank and look for minute flashes of light that happen when one of these neutrinos flies through this tank. So they're just trillions and trillions flying through the tank. But every now and then, one of these neutrinos, out of like the just trillions on trillions on trillions, every now and then one of them bumps into an electron through the weak force and sends the electron flying through the water super, super, super fast. And that makes the electron emit a very characteristic blue light, kind of a Cherenkov radiation blue light. It's like the sonic boom of the electron moving through the water in light. And you can see that, and you can infer there was a neutrino, and you can measure the neutrino. Crazy. We do an even crazier version of this where we want even more water, so we use the Antarctic ice. And you drill into the Antarctic ice, and your little detectors spread out on the Antarctic ice. It's a huge detector called IceCube. It's run partly out of University of Wisconsin-Madison, where I spent a couple years as a postdoc. It's crazy. And it all works. And when you do crazy things like that, you can see these crazy things called neutrinos, and you can actually take a picture of the core of the sun in neutrinos, and those can actually let you measure how fast nuclear reactions are happening in the core of the sun. Okay, so we could use like crazy nuclear physics to like observe the absolute core of the sun from the neutrinos that are flying out of it that think everything's transparent in the universe, practically. Okay, what's our other way of measuring things? So the other thing that can travel through the sun and all fluids is something that I'm using to talk to you right now. Right, the air between us is transparent to light, but it also it conducts another kind of wave through it. It conducts sound waves from my mouth to my microphone, which are then being sent electronically, and then they're coming out of the speakers that you're listening to. Sound waves can travel through fluids really well. We're actually, you may not think of it this way if you're not a fluid dynamicist, but you're actually sitting in a fluid right now. It's all around you. The air of our atmosphere is a fluid. And anytime you're in a fluid, like I'm swimming, I'm just very heavy compared to the air. So I sink, and I'm at the bottom of the swimming pool, basically, of air rising above me. But I can send sound waves through this fluid. And sometimes another wave called an internal gravity wave, but especially acoustic waves, sound waves through this fluid. And those sound waves can travel through this fluid. So the sun can actually have sound waves traveling through it. And if we look at the surface of the sun at this opaque photosphere, so again, like I am the core of the sun, my hands are the photosphere here, and we can see the photosphere of the sun. We can't see inside, but we can see this photosphere. And when we look at the photosphere, what we actually see is this. We don't see the photosphere just sitting here stable, quiet, and static. We see it actually rippling continuously. Okay, so once we had the data coming in, solar physicists started working with seismologists to figure out the math and the analysis to take this just utter mess of ripples and disentangle them and figure out like, okay, this particular wiggle, well, it traveled through this part of the sun, and this is what it saw on its way. What are the things you can measure? Well, you can measure how the frequencies of the wiggles shift, and you can measure, if you can disentangle all the wiggles, you can know which particular wave shape those came with. This is all linear physics, so this is stuff we're really, really, really good at doing. Like this is what you more or less spend all of your undergrad learning to do. And then like in graduate school, we're like, all right, like here's how to do it even more. And like linear physics, we're just super good at. Occasionally we're trying to do other problems. They're too hard, we come back to linear physics. So wave physics like this, linear physics, we're like, we can do super good at this when we like know where to begin solving the problem. When we don't, it's just a mess. But when we have some guidance, we can do super good. So you can figure out how the frequencies shift because the wave, like this wiggle, is traveling at a slightly different speed than this wiggle. They're both visible at the surface. Why are they traveling at slightly different speeds? Well, this wiggle went a little deeper in the sun based on its linear wave shape that it's got. And so it saw a part of the sun that was hot compared to this wiggle that stayed closer to the surface. So like, if here's my surface, one of the wiggles is like doing this, one of them's going way down deep, and the sun's hot deep in and cold near the top. 15 million degrees deep in, 6,000 degrees at the top, continuous gradient in between. So the ones that are deep in see higher temperatures. That shows up as faster sound speeds and slightly different frequencies. And you can actually measure the temperature of the sun in detail and with position going from the surface into the core. And that's one of these things that we can measure to like 0.1%. And we can actually measure it even better than that. So that's how we have some confidence that we can measure the inside of the sun. And that's how we have some confidence that our solar models, the physics inside the sun, is any good. That's why we have any confidence that the nuclear physics is right and that particle physics was wrong before we then found that out from other particle physics experiments. Okay.
Well, thank you so much, Ben. You're a trove of information. That pretty much covered everything that we wanted to talk about. I did, though, want to ask you one question. So we do a little thing we call Capcom Q&A, where we solicit questions from the public and bring those to our experts here. And there was one that came through that I did want to ask you because I thought it was really interesting. So Dennis from Texas wants to know, why do more sunspots let me hear radio stations from far away, but solar flares disrupt my listening?
Ooh.
This is something I've never heard of before, so I'm really interested in this.
And this was from Dennis. Is that?
Yeah.
So Dennis, this is a cool question. And it's actually, on some fundamental level, why we learned to love studying the sun at all, to study solar physics at all. So let me answer your question, and then let me tell you a cool little bit of history, because I'm a professor, so I talk all the time. Okay, so to answer your question, so there's a good chance that your faraway radio signals that you're seeing are probably coming off of bouncing off the ionosphere of the Earth. Okay, so the ionosphere is this layer of our atmosphere way high up that's a charged layer. And if you're down here on the surface and you send radio waves up, they hit this charged layer and it can act to reflect them and it can bounce them down. Okay, so we can use that to communicate long distances. AM radio does that, and so do some of the like hobbyist radio sorts of things, like ham radio and other stuff. This is how you can like get signals from like Antarctica to Colorado and do stuff like that too, right? So you bounce signals off the ionosphere or channel them in parts of the atmosphere up near the ionosphere. I don't know why sunspots make it easier to see better, but it's got to do with properties out of the ionosphere. And I have some ideas of what solar flares do. So when a solar flare goes off, so a solar flare is a just sudden release of a whole bunch of extremely energetic photons, X-rays, gamma rays, ultraviolet come streaming out of the sun all at once. When that pulse of like crazy energetic photons flies through space and hits the Earth's atmosphere, it does all sorts of things to ionosphere, and it changes the charge states, and it like changes the surface shapes of the ionosphere. It could be pushing it deeper in, it could be blowing parts of it off. I don't know. These are not things that I'm the right person to ask about, but I know that flares like mess up the ionosphere of the Earth. And when that, so do coronal mass ejections that can be associated with them, and like they do cool stuff to the upper layers. I think that what's happening is these storms, this nice layer that you're using to channel and bounce your radio waves off of, it's just being all messed up, and you can't get your signals from long distances anymore during these flare events.
Very cool. Well, I think that we are just about out of time. So we have been talking with Dr. Ben Brown, a fluid dynamicist and assistant professor at CU Boulder. Ben, thanks so much for being with us today.
Absolutely. And you can find me online through my faculty contacts. You're welcome to send me emails from the public as questions come up. I don't promise to respond to them in any timely fashion. I have 3 small children who I love very much, and do a couple of other things too. But I will try and respond to questions that come if people want to ask questions, or point people to other people who can actually answer those questions. So.
All right, and that wraps up another episode of A View from Earth, brought to you by the Fisk Planetarium. We'd like to thank our guests, Chris Gilly and Dr. Ben Brown, for giving us their time and talking solar physics with us. And I'd like to remind all of our listeners that the extended interviews of these, the extended version of these interviews are available on YouTube and SoundCloud. So if either of those really sparked your interest, you can check out the longer, fuller edition for more juicy solar physics. Next week is going to be a lot of fun. Join us for a conversation about the moon and what it might take to live there with Dr. Paul Hain and Dr. Margaret Landis. Just a reminder that you can send us your questions for us to pass on to our experts in the Capcom Q&A segment. You can do that either by filling out a form on our website, colorado.edu/Fisk, or by sending us an email directly at fiskpodcast@colorado.edu. Make sure to subscribe to this podcast wherever you're listening so that you don't miss any episodes. And this podcast is available on YouTube, SoundCloud, Apple Podcasts, and Spotify. From us here at A View from Earth, thank you for listening.